If you've watched the two videos on electricity, then this is really just the last bit to cover, and that is characteristics IV graphs. And what I mean by IV graphs are current voltage graphs. Now we're going to look at the characteristics of three specific type of components, and one of them is the light bulb. One of them is a piece of wire or a resistor. They both behave the same way. And the other is a diode. And you need to be familiar with the shape of these graphs and how they're and what that graph suggests about their nature. Well, first things first, you're going to have to set up a circuit, and the circuit is looking to measure the voltage around this component. So those dots are where you'd attach the component, and you're looking for the voltage. So importantly, you have to attach the voltmeter in parallel. You're looking for the current, so you attach the ammeter in series, and if I were to connect these two together, then that would yield a voltage and a current. However, what you're interested in is looking at how the current changes with the voltage. So you need to somehow change the voltage and the current in this circuit. You could either do it by changing the number of cells, or you can do it by changing the current in the circuit by having a variable resistor. As I change the resistance here, so some of the voltage share will go across here and the remainder across there. So that's how you start to control the voltage. Okay, so that's how you set up the circuit. Now, what we are changing about the circuit when we investigate this is the voltage. So I'm going to change this until I get a certain voltage. And what I'm measuring is going to be the current. And I'm sure you're familiar with those terms. What I'm changing gives rise to the independent variable, whereas what I'm measuring gives rise to the dependent variable. And when we're dealing with graphs, because you will have a table of results, of course, but I'm not going to write down any random table here, they should yield the following graphs. Voltage, because it's the independent, is always on the x-axis, or we could even call it, if you like, the potential difference to be more precise. And the current, which is measured in amps, is on the y-axis because it's the dependent variable, that's what I'm measuring. The IV curves. Now, first of all, for a piece of wire, or even a resistor, we have nice linear behavior. This is directly proportional. And what does that mean? Well, it means it obeys Ohm's law. It means that it has a constant resistance, or even that it obeys the equation V equals I times R, which we've covered in the previous videos. Right, well, what about another one? What about if we looked at the light bulb? Well, if you look at that, it starts out looking about the same, and then suddenly it starts to curve off. In other words, characteristic IV curve, if you like. This is a bulb. So what does that say? Well, it's not obeying Ohm's law. I mean, interestingly, Ohm's law, if this is a constant resistance, then something that's down here has a higher resistance, and something along here has a lower resistance. What that suggests is we have a low resistance initially with the light bulb going to a higher resistance. So with the light bulb, we have an increasing resistance. Why? Well, what we say is with the light bulb, it's getting very hot, the wire has. So as you increase the voltage, so the current increases, so the heat increases. So you can say increasing resistance because the wire, sorry, the bulb gets hotter. So it's getting hotter, you're increasing the resistance. And there might be situations where you might have to work that out. You might take 2 points, for instance. Let's take these 2 points. I'm going to put some very random values in here. And let's say initial voltage of 2 volts and 8 volts. And I take a current of, let's say there is 0.1 of an amp flowing through and 0.2 of an amp flowing through there. Okay, what's the resistance at point 1, or as we call it, the cold point, because when it's getting hotter as you increase the resistance at point 2, which is hot. So resistance at point 1 is going to be voltage divided by current, 2 divided by 0.1, giving me 20 ohms. What about the resistance at point 2? I've got 8 volts and 0.2, so therefore we have voltage over current, which gives me 8 over 0.2, giving me, if I'm not very much mistaken, 40 ohms. So you can see this has a hotter, so the resistance is higher than the resistance here. R2 is greater than R1. So bear that in mind and explain why. It's an increase in resistance because it gets hotter. And if you'd like to understand why that might be, if you imagine these a metallic bond is this lattice of positive ions in a metal, and the electrons find their way through somehow. If it's hotter, the ions vibrate more and therefore impede the electrons. So that's the reason why. Okay, we're not done yet, because there is one last one to deal with, and that is with a diode. And with a diode, our current voltage graph looks very much like this. It flatlines, and at a certain voltage it suddenly increases rapidly. It's about 0.7 volts. This is for a diode. And interestingly, if we inverted the connection, so we turn it round, this stays flat all the way. That should be it. Stays at 0 amps. So what does it suggest? Two things. One is that it only allows current to flow in one direction. And the second point is it acts like a switch. Turning on at 0.7 volts. So it acts like a switch, and nothing really happens, then suddenly 2.7 volts happens, and suddenly it allows current to flow, quite considerably allows current to flow. This is the symbol for a diode. It only lets current flow in that direction. It will stop current flowing if it attempts to go in that direction. So the IV curve for a diode. Superb. Okay, I think that's all for the characteristics. You've got the experiment, how you'd set up the experiment, and then you're familiar with the three types of IV curve. And you're happy that, I mean, this has, in effect, because it's a flat line, an infinite resistance, then suddenly a very, very low resistance. It switches on. Okay, brilliant.